Very quickly, Jeroen Borst, I'm sure that you will introduce yourself further, but you are a program manager, digitalization for livability and accessibility at TNO. As I understand, we know each other already from the early days when your urban strategy was still framed as a serious game, and we were both heavily interested in that. So I'm very much looking forward in seeing how we transgressed from serious gaming to digital twins, huh?
Exactly.
But we will start the talk, as I understand, with the first speaker, which is Guido van Gageldonk, who is a CTO and co-founder of Perspective. And I'm sure that you will explain what Perspective is and does. Yeah. And you present yourself on social media as a digital twin and industrial metaverse evangelist.
Correct.
Right? Oh, correct.
Yes.
So I would say take the floor, Guido, and evangelize us on digital twins.
So let me start up the presentation. First check, can you all see the presentation? Only
we
one.
Can see it.
Yes. So yeah, as said, I am the CTO of Perspective. Perspective is a company from Eindhoven. We have a global reach, and we work together with Unity 3D, which is also a global company. And that's where I will explain some things on what we do with digital twins. And this topic is mainly focused on how that is applied in manufacturing. So in producing new products and creating new production lines, for example. As we all know, we want a more sustainable world. And our vision is, and I think the vision of digital twins is that technology can help there, so that we can do more and more in the digital world, saving, let's say, carbon, but also actual materials in the actual world, and use the lessons of the virtual models as good as possible. So virtualization on itself, of course, is nothing new. Digitalization also not. It's more or less that we are in an evolution, and digital twin is more or less an evolution step in this digitalization. And that can help to do better sustainable manufacturing. So using the power of, let's say, simulation technologies and extending those capabilities into what you could call a virtual model or digital twin. And that's also what we do, and not only we, but also, of course, competitors like us do. But what has become really a tool and also a kind of theory and technology which can be applied, for example, in the manufacturing domain. So what do we mean with a digital twin? We try to, together with our clients, but also our clients build themselves with tools, to build virtual representations of actual systems as close to reality as possible. So that also means putting it in VR and AR, but also fusing different kind of levels of physics, visualization, all in, let's say, one integral model that you can then use to do all kinds of stuff with testing, training, whatever you want it to be. On itself, of course, digital twins are not new. I hear by reference Michael W. Greaves, one of the biggest professors in the world, and also the inventor of the term digital twin from the US. And of course, at NASA, it's already common practice to make more or less virtual models of as much as you can do. So let's say of rockets and stuff like that. But in the last 20 to 10 years, technology on, let's say, computational level has also come to the level that you can do more and more of this, and also cheaper, so that also for normal manufacturing, it becomes really valuable. And the aim there is to take away inefficiencies. So when we develop stuff, products, systems, machines, entire factory floors, we of course do a lot of inefficiency yet. So that means with stakeholders, we don't have clear pictures when we try to convey an image we have in our mind to somebody else, but also we sometimes have as people a wrong model of the world. That's an inefficiency. And those are things that you can try to solve by creating a digital world or a digital model. On itself, that's nothing new. CAD 3D modeling is, let's say, 30, 40 years old. But now you can do more and more. You can hook in more simulation and more data so that you have a richer and more complete picture of your world model. And that helps to convey your insights. A small clip. So good to understand is that what we propagate is also, let's say, the next step or an evolutionary step in computing technology, so simulation technology. So what we bring and also competitors bring to the market is real-time 3D technology. So most of you probably already know that you can make a 3D drawing, you can make an analysis, you can do simulation, but more or less the new thing for the last 10 years, which has come online, is real-time 3D, in which you can combine them together to have more or less a virtual model, virtual prototype, virtual system, which can really convey what it is actually doing, so that you can flip a switch and more or less have virtual steel acting itself out. That's what you see here. So in that sense, it stands on the shoulders of the old technology, and it uses this old technology also as the resources. So you use 3D models, you use simulation models, and you combine them into more integral models, digital twins. And I'll just small clip to show some examples. So that hopefully already gives you some insights in what it actually can mean. And where it comes from is, of course, the fact that in the past, we more or less siloed the work in engineering new systems due to the more efficient way of working. So you have mechatronical engineers, you have software engineers, you have mechanical and mechatronics. And now this gives a possibility, this new kind of approach to combine the modalities. So if you have a CAD file, you can connect it to logic and you can connect it to physics. And you can flip a switch and you have the actual system. And that what you have built can then later be used once the systems go into the field to also monitor data and collect data on and to do extrapolation on it. And it's, in our opinion, also very important to mention the fact that this also has a very high communicative value. So it's not only simulation value or emulation value or twinning, but it's also communicating an integral model. So integral models of all the disciplines, so that we can more or less overcome the Tower of Babel problem, which we now sometimes have in developing new cyber-physical systems like a wave stepper or a CT scanner and stuff like that, and production lines. And in that sense, it gives rise to what's, of course, already, let's say, common practice in software development, an agile approach, but then in hardware, so that you more or less create virtual steel and virtual models, which you can use like you use software. So you can create them, let's say, on a weekly or daily basis, and have prototypes, virtual mockups on a daily basis, and test more and have more communication on them and collect more information on those. And of course, that's a sustainability aspect of that. The virtual part of it means less travel, for example, clearer communication, but also more testing and let's say better testing, also infusing the information out of the field into these models. The interesting thing is, of course, we have been talking about this quite a lot in the last 10 years. And we most of the times talk about, let's say, step 6, about adaptability. So infusing this already with AI and stuff like that. But the honest answer is that most companies, let's say industrial companies and also manufacturing companies, are not there yet. So there is a quite big gap between what we have as data sets and what we try to achieve together with people and clients and also companies in the world. But we see that you can guide them through that process. So visibility and transparency are most of the times things that they can grasp quite quickly, because they most of the time already have things like 3D models and they have some understanding of their systems. So the integration is possible and they can start. And that also leads to the fact that digital twin itself is, let's say, a hype term. And it is, of course, comprises out of multiple use cases. And we see that, for example, in manufacturing, 3 main use cases come online quite often. So that one is system configuration, one is virtual testing, and the other one is dashboarding, and also, let's say, predictive maintenance. And here you see how this helps clients. So what it tries to do is to create this model, which is not only a 3D file, but it's also the behavior and has some world model inspiration, so it understands some physics. Then you can really try to create Lego blocks, for example, of a factory. And then you can really build this virtual Lego, like, for example, in Roblox or in Minecraft, but then on a factory shop floor. And this is how that could look like, or how that looks like. So I think you can understand how that can be beneficial and saves you time, money, and effort. So it's more sustainable. And also good, more technical, but to understand this now, as what I said, the new thing more or less in technology is that you now can combine multiple modalities. So you can combine this into a full integral virtual model, which you can use. And an interesting use case, for example, is we also are a supplier of the digital twin lab of the Technical University in Eindhoven. And for example, this means that students themselves build digital twins of systems so that they also can do virtual testing. So they can test a new system before it's being built, but also test their code, so the behavior. And I will skip it a bit because, of course, this works together with the actual system. So they can use this to look already at faults before they're going to make this setup, but they can also collect data on it and visualize it on the virtual model. And this was, by the way, also a case in COVID, so that they could test without actually going to the lab because they could not visit the lab due to the COVID rules. And this is also what a lot of our clients nowadays do. This can save them flight time, so they can do more and more, of course, on behind their own PC instead of the side of the client. And in our opinion, so looking into the digital metaverse for industry, for example, we propagate openness. So the fact that you can interface these objects and this world with other tools and even competing tools, so that you have this, let's say, interwoven web of virtual models which you can use. I think, of course, it's interesting for most of you to see actual use cases of clients using this kind of technologies. One is Toyota material handling, and that means that they do prototyping of such setups. They can do testing. They can have, let's say, what you could call hardware in the loop. So the hardware has no clue that there is not an actual machine here. It talks to a virtual machine, in this case, a virtual simulation. And you can do all kinds of design reviews, testing, but also, of course, use this system still once it's in the field to, for example, look at why are we in a fault state, for example. That is what this kind of new models bring those clients. So that means that we the models are connected to, let's say, the physical world, in this sense, to data in the actual world. So the data on an actual system deriving such a machine or a robot or a factory, and it's then connected to its virtual counterpart so that they can communicate even with each other and stuff like an edge. And here you see that, for example, also in cobots. So collaborative robots are, of course, also becoming more and more important. And then it's very interesting that you can, of course, also step into this virtual world and play with this virtual robot before you, for example, execute systems in the real world in which you could even hurt a person, for example. So you can build this fully virtual. Let's try to skip to a part where the robots are in motion. So the robots move and act out. So this is not animation, this is simulation and all real time. So it is like it would act in the actual world as well. And you can step into this in the VR and also turn in a screw and take out a screw, for example. Another interesting thing is, of course, doing a lot of virtual testing, prototyping. So that's actually what Philips uses it for in the entire fullness of the capability. Philips has built a fully virtual version of their CT, MRI, and X-ray systems so that they can test this in a lab. A small clip on that. I will skip the audio, but here you see the virtual system. The table runs into a virtual world in which you can have physicians already practicing with this virtual model, in which you can do design reviews on the model. But they also do, for example, tests of the software on all the different configurations they have. Philips has 300 different kind of configurations of this system. And of course, building them all physically would take a lot of time, and also testing it on site will cost a lot of flight time. These are the things that they can save on by doing this in a virtual model and create this kind of digital object, digital twin, which fuses this modality. So the 3D with the behavior, with also the world model onto one virtual simulated object, which they also use to, of course, check if a system is in a fault state in the field. What does it then mean if we put that on the virtual system? And in that case, Philips themselves say that it saves them about 260K per system. So it's also bringing back really the money impact of using this kind of technology. It was maybe a gimmick, let's say a few years ago, but it really saves a lot of total cost of ownership of systems. And then also going into the dashboarding setups. The thing is, with this kind of technology, you can go further than normal manufacturing systems, but also with rich visualization. So you can actually visualize the state of the plant as is, if you have a data lake in place, which has, of course, collected the data. So that brings us back to the picture of the TNO Aachen part, in which some companies are not here yet. And it's, of course, a digitalization process. But then you can also mine this 3D visualization data, and you can also give your workers, or the people on the shop floor, a richer and better understanding what's actually happening around them, what's expected from them, and what they are working on. So they can really visualize and see what should be done and how is it being done on the shop floor approach. And if you then combine all these powers, that brings more or less the capability of building autonomous plants. So one could understand that if you want to do what, of course, for example, Tesla is trying to do with a car, but then on a plant level. So Tesla and Waymo, who are both trying to build autonomous cars, use digital twins at an extensive amount to test the behavior of the cars. But if you want to build a virtual of an autonomous plant, you should do similar things. You want to try to do as much training and development in this virtual model, because it will be a very expensive exercise to do this only in the actual domain. So if you work with robots, autonomous moving vehicles, as you see here, you can train them, of course, in this virtual space before you put this on the actual shop floor and start to execute this. And that's, in our opinion, a short, let's say, sneak peek and introduction in digitalization and digital twins in manufacturing context. So that's my presentation for now.
Okay. Thank you very much, Guido. That was very insightful, also very much to the point. I'm sure that everybody here is now full of questions and things to pick up. But for reasons of time, I would actually suggest to stick to the plan, and please keep these questions. And I would like to invite Jeroen to share his perspective on digital twins. Also stick to 20 minutes so that we have another, 15, 20 minutes for some Q&A. Thank you again, Guido, and the floor is up to Jeroen.
Thank you. First check is, can you see my screen, and am I audible?
We can see your screen very well. It's not in presentation mode yet. The audio, I can hear you, but you're not very loud or clear. So you're a bit at the background with your voice. Now I think you're going into presentation mode, but I see your notes. Yeah, this is
Is it
okay.
better now? Is my audio better now?
Both of them are much better.
Okay. Then I can start my video again so you can see my face. Yeah. Okay. Excellent. Yeah, it's always good to check because it's Zoom, it's not Teams, and then it's different. And yeah. Okay. So my name is Jeroen Borst. I work at TNO, well, already for a long time now, on, you could say, urban planning. And you could say 20 years ago, we built noise maps or traffic simulations in GIS systems. And finding out that if you start, well, if you try to convey information to stakeholders, to cities, the immediate questions that they have is, okay, what happens if? What happens if I build up areas, if I close down roads, whatever? And then my answer 20 years ago was, okay, that's a new question. I have to go back to the lab, so to say, do a new calculation, and in, let's say, 6 weeks, you get the answer. But if you look at the process of urban planning, that's like interaction. People want to see, want to interact with each other, want to see immediate results. That's why we said, okay, we have to build something, and the term digital twin, I hadn't heard of it yet. It didn't exist yet. I think we started to call it a serious game, Igor. How to interact with your data of your city in order to well, to get immediate feedback. And the type of questions that we see from cities are, you could say, from here and now, cities questions like today, how to plan multiple roadworks, for instance. If you bear in mind that if the city of Amsterdam, for instance, closes down one road in the network because they have to do maintenance on a bridge, it takes them about 8 hours to do one calculation to see the impact only on mobility. And then given the fact that basically all the quays and bridges in the center of Amsterdam have to be maintained over the coming years, planning multiple of these roadworks is an immense task if you have these calculation times with the traditional methods. So that's one of the, you could say, one of the reasons why you have to speed up calculation. But another one is, and Guido was already mentioning that, somehow you need to interact with your stakeholders to visualize what is happening and to do that integrally. So if you look at questions like, what is the effect of lowering the speed limits in the city? Does it improve air quality, or does it get worse on some places? Or what is the impact of shared vehicles? Or, well, in the further future, what if we have autonomous cars, AVs, in other words, robo-taxis? Will it help the city to be more accessible, or do you see other effects? So to see how to shape the city, how to help them in the battle for space, because all these transitions in energy, mobility, sustainability have to take place in that same built environment, we built what we call now digital city twins, very fast simulations connected to visualizations, in order to be able to literally stand around the table with stakeholders. In the central picture here, you see different agencies in Singapore standing around the visualization of their city. And actually in this session, finding out that different agencies, the Urban Redevelopment Agency in charge of urban planning, together with the Land Transport Authority, together with the National Housing Agency, were actually active in the same areas, in the same domains, not knowing it from each other, only until they saw, you could say, our digital twin. And then next step, they wanted to, you could say, play around with it and see, okay, but if you do this development and I do that development, you build new houses. I want to limit the amount of asphalt in order to make place for cycling, for instance, do we run into a problem or not? And so that is the type of interaction that we seek. In order to make that possible, we built an architecture, you could say a new approach of how to connect models on the one hand, interfaces on the other hand, so how to interact with that system, and data. And when we started to work with this, our starting point was, well, let's see if we can connect available open source or commercially off-the-shelf products, glue them together, and see if we can make it work with the ambition to make it interactive, real-time, if you like. And then you could say step by step, because the complexity of a digital twin of a city as a whole is so big, that we really have to crank up the speed of the computation. So we started to do the simulations of, as I mentioned earlier, noise models or transportation models. We made them using GPUs, so graphical processing units, way much faster than the current state of the art. And then you have to think of getting calculation times down from 24 hours to 2 minutes, so a factor 1,000 or something, thanks to extreme parallelization on these graphical processing units. But if you have so much calculation power and you run so many, you could say, changes through your system, your data solution, and we started with a traditional database, I won't mention the make, but a very well-known commercial database. Such a solution is only busy indexing, trying to keep up with the changes, so to say. So immediately the data solution becomes limiting. And therefore we decided to implement, you could say, the Google protobuf description that they have. They have open source, they have their way of communication and distribute the storage of data. And we implement it ourselves. And that means basically that you leave all your data basically where it is, and you only machine to machine transfer that data element that is needed for your calculation. And that speeds up the process immensely. And then the third factor are the interfaces. And if you take traditional interfaces, 3D, we also saw that it's quite a challenge to have these interfaces to keep up with the changes. So it's, you could say it's, well, common technology to do rendering and then show, but to actually interact with large amount of changing data, that was also a challenge that we saw. So we on these 3 points, we have been very active to bring together, you could say, the ICT knowledge with the domain knowledge that we have within TNO. And then, speaking of which, what we bring together now in the digital city twin is the knowledge that we have on mobility, starting with mobility demand. So, or actually behind that, what are the activity patterns of people in the city? What does the population look like? What are the activity patterns and what kind of mobility demand arises from that? And then if we confront that with all the mobility options that are there, so the car network, of course, but also public transport, shared mobility, mass, or if you like, in the future, automated vehicles, we can predict the amount of trips per modality, as we call it. So then you get traffic intensities or amount of people in public transport. And from that, we can calculate the impact on environment. So the amount of air pollution resulting from car movements or noise from all the cars as well, combined with other sources, because we want to create an integral picture. And then well, in the last years, becoming more and more important is the transition towards sustainable energy, and that is on two sides of the story. One, the production of local energy, solar panels, wind turbines, especially solar in cities, is becoming a challenge because now we see not only congestion on the road network, but also on the power grid, on the electricity grid. On the other hand, the mobility is also electrifying. So more and more cars becoming electric. I will show an example of Singapore making the transition from diesel buses to 6,000 electric buses in one city. So there you see an interaction between, you could say, the mobility system and the energy system. How do you blend it in combination? And then well, arising from all these activities, you get a climate impact, global warming potential. Nowadays, we're also looking at climate adaptation. So how robust is our network to changes due to climate? And the last part is how do people respond to changes in well, in their environment, the environmental exposure, as well as changes in accessibility, for instance. All parts of, you could say, broad welfare. Come back to that later. And then a short movie clip of what it looks like. And this is, people might recognize it already, is the city of Amsterdam. Well, here we see a visualization, 3D. Maybe you could say it's a low level of detail. But the nice thing of it is that we can project the outcomes of calculations of, you saw noise, now you see air pollution on a city level. And then, well, still just a visualization is, well, there are many more examples of that. But the uniqueness of the technology that we have is that you can actually interact with it. And we are especially proud of our collaboration with Amsterdam, because Amsterdam is using this digital twin well, in daily business to see what the effects of roadworks or new spatial plans is on their city, and they can do the scan of the impact very quickly. And this is an example of a simulation of closing down the ring road, the A10, on the south axis, the Zuidas, in Amsterdam. You can create a control, as we call it, on every data object in the digital twin, and you can describe how the properties of such a data element are changed. And here you could say the accessibility of one link in the entire system is changed, and immediately the traffic flow of the entire city has changed. And you can see that in some parts it becomes more busy, some parts it becomes more quiet, and that also has an effect on noise and air quality, for instance. So this is basically how cities can interact with such measures. And you could say these are the easy ones, what they do on a day-to-day. But there are also examples where the interactions are a bit more complex than that. So basically what we do with these digital twins is to offer integral urban planning to the city, and in this case Amsterdam. And the questions that where they started with is, okay, what happens if the city densifies enormous amount, like 90,000 extra dwellings within the city ring are to be planned. That's a city within the city, you could say. It's like the city of Leiden to be pushed within the municipal borders. That will have an immense effect on all the subsystems, and they want to get that insight. But also to look at the impact of shared mobility, for instance. Basically, every city wants to become car light, limit the amount of cars. You could say the paradox is that they want to provide shared mobility, so extra cars, to limit the amount of cars in the city as an end result. But because of this paradox, it's very important how to dimension, you could say, the shared mobility proposition. So with all the knowledge that we have on the usage of the different transportation modalities, well, we can help them with that. And same goes, I will go through it very quickly, for the NS, so the Dutch Rail, to see how we can help them, well, to, you could say, increase usage of trains, especially outside of rush hour. We apply it in many places in the world, but I will go through it quickly. One example that I want to show very quickly, it's in the news right now, is that when you look at mobility, you can look at, you could say, the KPIs of mobility, how many people use public transport, for instance, or how is the model shift between car, or the model share between car and public transport. What we see when you look at those averages, many of these investments in transportation have the tendency to leave behind, you could say, the people with the lower economic status. And we see that very much on the island of Curacao. People who are dependent on the bus, who cannot afford a car, also literally have a long distance to the labor market. So it's difficult for them to get a job. So, and by building the digital twin, also with local knowledge, so from the university, we help them to design the mobility system in such a way that also people, you could say, underserved communities also get access to the labor market. You can say that is something for developing countries such as Curacao. You can consider it literally as a developing country, but also in the Netherlands, we basically see the same. I will go through it very quickly, but the mobility patterns of highly educated people is really different than that from, you could say, practically skilled people. And
Jeroen, I am sure that everybody in the audience now is burning with questions.
Okay.
And looking at the time, we have about 45 minutes for the Q&A.
Okay.
So if you, it's maybe good to wrap up so that we can also have some discussion.
Yeah, thank you. Thank you.
Yeah, sorry. It's all a bit rushed, but this is just briefings and
yeah. No, but basically my presentation ends here. That this challenge, we also see it's a bit more hidden, but we have the same challenges in the Netherlands as well. And I would like to leave it with that. Thank you.
Thank you, Jeroen. Very insightful. Well, I would like to open the floor for questions from the audience. And I have one request. Please try to ask short questions. And also for the speakers, try to give short answers so that at least we can have a lot of questions. And then if the questions are depleted, you can take a bit more time. Who wants to start? I see a hand. Bram, go ahead.
Yes, Jeroen, Guido, very interesting presentation. It was very great to watch. Guido, I had a question. So I saw a lot of simulations regarding robots and production facilities, and you talked a lot about using data. Do you guys also run a lot of simulations using, for example, machine learning techniques like reinforcement learning?
Yeah, so we ourselves, not that much, but our clients, of course, do this. So the thing is, of course, that in our case, we use Unity 3D, so that can directly be connected to stuff like TensorFlow. So then you can start to do reinforcement learning. The thing, of course, what we more or less first provide is the fact that you first have to build a model in which you want to do learning on, because that's where most people go wrong. they say, but I can do AI on this. Yeah, but you don't understand your world model. So first, you have to offload your world model, or at least what you think the world does, for example, in the case of a robot or an AMR, to this virtual domain. And then you can start to try also enforced learning on that.
Cool. Yeah, we do something similar. We teach something similar to our students. We also give them a simulation. They have to do reinforcement learning with robots to train them over, multiple sessions. But cool.
Yeah, so the things you saw, of course, that are also cases of clients which do that. So then they implement learning algorithms on that as well.
Okay, cool. Can
Thank you
I
very
maybe
much.
send you a message after, because it might be interesting to connect up for some future projects.
Yes, of course. No
Cool.
problem.
Okay, thank you. Anyone else? Nick.
Yes, thank you both for very good presentations. What I was wondering, how do you map something complex as behavior, especially when it comes to mobility? That's a huge cultural aspect. Mobility is very different in the Netherlands as it is in Curaçao. How do you estimate that? And do you also use real-world data to validate this information?
Yeah, that's a good question. And it also maybe links a bit to the previous question. What we do is, another part of our work is we try to understand, you could say, choice behavior. We model choice behavior of people. And you could say we try to increase the amount of detail, so more descriptors of the people, of the population, more micro data from CBS, but it also requires, you could say, more information on the mobility or activity patterns of people. So basically any data set that we can get our hands on, you could say, experiments of new mobility propositions, we use to translate that using machine learning as well into what we call utility functions, describing, you could say, the value of one option in relation to another. And that way of choice modeling is what we implement to describe this complex behavior of people.
Okay, very interesting. Thank you.
Another question. Then I go. Jeroen, or both of you actually, I think you're familiar with the fact that I come from the serious gaming tradition. Jeroen, we talked about integrated simulations and serious gaming.
Yeah.
Looking at these tools. So where is the gaming part? I see a lot of people playing with the tools. But also for Guido, I can understand that it's also a tool to facilitate the communication and interaction between different stakeholders. So is there still something in it that looks like a game? And should we still look at gaming as to create interaction? And how has it changed as 10 years ago, Jeroen, when we started doing these things, or 20 years?
I think, the shortest answer is if I get a 1 minute pitch of what we are doing, is that we say we build SimCity for professionals. Mm-hmm. And everybody understands then what we mean. So, but to be honest, it's still, you could say, a very elaborate simulation that we built. Mm-hmm. And there's still work to do to build the gaming element into it. So something like competition or playing against a challenge, for instance. It's actually the real world challenge that you're playing against, you could say.
Yeah. Guido, any take from you on this?
Yeah, so the interesting first thing is, of course, that we work together with Unity 3D, which is one of the biggest gaming engines in the world. So we are their verified solution partner for industry. And in short, we more or less try to build Roller Coaster Tycoon or Roblox or Minecraft for industry. But in our case, it's more playful aspects to it. So to make things easier for people to build and convey their concepts. And of course, sometimes in training elements, which we not build, but people can build with our tools, they also insert, let's say, reward kind of systems. But I think, we use gaming technology as a cornerstone. So that's also the thing. But B, playfulness is more or less in the communication, so that people have easier and quicker things so that they can show to others. So it's really that, in that sense, that part integration.
If you look at each other's presentations and work, so is there something that strikes you as, of course, very obviously similar or something like that, but maybe even more interesting, the different words where you work in, where is the difference in using digital twins, and if there is any difference? I don't know.
The scale, of course. I hear a lot of similarities actually, and also in the approach. I mean, we use different words. The visualization is maybe different, but you could say the basic approach, I see many similarities. Maybe what?
Yeah, I think scale is, of course, let's say, relative. So, and that's the thing. I think we both have to work with let's say, data sets which have direct interplay with each other. And that's, for example, in the case of VL Netcar, we do an entire factory shop floor with all the interactions that are there. It's similar to a full city with, let's say, a level of detail of interaction of traffic. So in that sense, the way we have to compute, the way we have to set up models, it's probably the same to make choices on level of details, interaction levels, and stuff like that.
Okay, I see some more questions now in the audience, which is very good. And first one on my screen is Marco Kjaer. So Marco, go ahead.
Don't know if you can hear me, but
well.
I had a question for both of you. If you had any ideas for multi-tier or twin-to-twin architectures, and what do you think about those architectures, especially in a city planning perspective?
I don't know if I get the question fully correctly, but what my opinion is on software architectures.
Like I've been reading a lot about lately the multi-tier or the twin-to-twin, at least I've been seen it.
Okay, yeah, that is quite a subject. We're in the middle of it in the Netherlands right now, and it is a good point. Where to start? You could say that every digital twin, as I presented, becomes, you could say, a data product of its own. It becomes you could say, an element that can communicate or be nested in a next level digital twin. For instance, the digital twin of a city, nesting in that one of the region or of the country, if you like.
Yeah.
Giving an extra element of challenge when it comes to data sovereignty, for instance, because when you do that, it's not only, you could say, as an ICT problem, but it's also a governance problem. Who owns the data, especially when one product feeds into another one. So we are building on that. Guarding, you could say, the data sovereignty of every data element that is in these digital twins. Also safeguarding privacy. We didn't address that yet, but yeah. Actually, I don't know where to start to answer.
Maybe something for a follow-up discussion.
Exactly. Yeah.
If anything. Okay. I also saw a question in the chat from Niels. Maybe you want to just raise the question. Yeah. Hi, Niels.
Hello. Hi. Good afternoon, everyone. My name is Niels, and I'm with Cyclomedia. To give a little bit of context, I saw a lot of visualizations in your presentation, a lot of gray blocks and lines and everything. It looked a bit 2D and 3D combined. But I focused mainly on photorealistic visualizations for most of my work. I think, Jeroen, we've spoken to each other before. I was really interested to see if the visualizations would either improve your simulation and analytical platform, or would it hinder the simulation or analytical platform in terms of data management? I can imagine it might hinder it a little bit because of file sizes, but I'm really looking forward to hear your perspective.
Multiple answers. It's very dependent upon the use case. If you do city planning and you want to look at the mobility patterns, for instance, having a very high level of detail, we found out that it's more like a hindrance than because it distracts you from the actual topic that you want to convey. But immediately, when you look at placemaking, for instance, how comfortable will it be in a certain place if we change something? That is a very hot topic when it comes to cities. Then visualization and realistic visualization becomes very, very important. So it's very dependent on the topic. And actually, our focus has been more on the first, and is now recently shifting back again to the realistic visualization. Actually, we see the importance and the value of it.
Okay, thank you.
Thank you.
Mark, you had a hand raised.
Yes, I'm curious if you, well, actually what you just said, Jeroen, if you want to go to the level where people individually can interact with the simulations or the twins you're constructing, what do you think is important that we would focus on in our research now?
If people can interact with it individually.
Yes, so I can walk literally myself through your virtual your twin of the city.
Yeah.
This is the...
Yeah, I mean that is not the hard part, so to say. But if people if you enable people to make changes in the data, which is also possible, they can make their own, you could say, propositions of road closures, new playgrounds, whatever. Then is to keep the scenarios consistent, to moderate that. That's the actual challenge. ICT, it's no problem. I mean, we can allow as many users to the same platform as we like, but to keep the story consistent, so it's more like a governance issue than an ICT issue, you could say.
Okay, thank you.
Yeah.
No, we
I
have
a bit of related.
Yeah, sorry.
I have a related question to Guido, because you mentioned also something about building digital twins for cobots. And with cobots, then there also the human is in the loop. What are the challenges there? Do you want to involve real people in these simulations, or do you want to model people, or?
Both. Of course, that's probably on all levels the both things. You want, of course, first you do an assumption of, let's say, the agent avatar model, and you also later want you in parallel you want to have a data set of actual people interacting with this virtual model. The virtual model, because of course the actual system can hurt people if it is not calibrated correctly, and then start a feedback loop. So then your agent avatar becomes better because you close the delta between what you record of people in this VR setup or even the actual use with the actual cobots, and then they feed on each other.
Okay. And looking at the time, and time flies when you're having fun. I would like to stick to the 1 hour and take the opportunity to thank Jeroen and Guido very, very much for your wonderful presentation. It was really straight to the point, focused, very insightful. I'm sure we have a lot more questions, but we can contact you. You can contact us. I also would like to thank the participants, the audience, for taking their time and the interest to join this meeting. I do want to pre-announce that the third DIGIREAL lunch meeting will be about virtual humans. And Nick, that will be on
the first Thursday of every month. We have this meeting, and
okay.
2nd of December.
So in a month. Also a very, very exciting topic, and there is also definitely complementarity between virtual humans, virtual social spaces as the metaverse, and digital twins, which is exactly why we have this program, DIGIREAL, together with a lot of partners. I want to thank MindLabs also for organizing with it. I think we're getting into the flow on setting this up. Thank you very much. I'm looking forward to seeing you again. Well, goodbye.